Ever wondered how security experts find a secret code? I mean, one that's used by governments and banks, hiding deep inside a computer program? Well, today we're putting on our detective hats. We're going on a digital investigation to find the world's most popular secret code, AES.
So let's start with the biggest question of our case. How do you actually spot a super sophisticated encryption algorithm that's buried under millions of lines of code? I mean, it sounds almost impossible, like finding a needle in a digital haystack. But it turns out there are always clues.
All right, let's get into it. Our mission, should we choose to accept it, is to learn how to identify the signature moves of AES. And look, this isn't just some fun thought experiment. This is an absolutely crucial skill for security researchers who are hunting down malware, or for engineers who need to double-check that a product's security is actually working the way it's supposed to.
And that brings us right to our main person of interest, or I guess our algorithm of interest. It's time to formally meet the suspect, the Advanced Encryption Standard. But everyone just calls it AES.
So, what is AES? Well, think of it as the current heavyweight champion of data encryption. It's the global gold standard. See, its predecessor, an older code called DES, was starting to show its age. So the U.S. National Institute of Standards and Technology held this big public competition to find a replacement. And the winner, a brilliant algorithm originally named Rinjendal, was crowned the new king, AES.
Now, here's the core idea behind why AES is so tough. It's not a one-and-done kind of shuffle. No way. It takes your data in these little 16-byte chunks, which we call blocks, and then it puts them through a whole series of intense, repetitive transformations called rounds.
And you can see right here how its security just ramps up. The strength of AES really comes down to two things: how long its secret key is and how many of these rounds it performs. As you can see, a longer key means more rounds of scrambling. A 128-bit key, that's 10 rounds. But jump up to a 256-bit key, and you're going through 14 rounds. And trust me, each one of those extra rounds makes the encryption exponentially harder to crack. Okay, so we've got the basics down. Now, let's get into the nitty-gritty. Let's investigate our suspect's MO, its modus operandi. What exactly is going on inside one of these super important rounds? So, first things first. AES takes that 16-byte block of data and neatly arranges it into a 4x4 grid. This grid has a special name, the state. Now, for our investigation, I want you to picture this state as a little tray holding 16 perfectly arranged ingredients, and we're about to scramble them into a dish that is totally unrecognizable.
Just about every single round of AES encryption uses these 4 distinct steps, always in this exact order. You can think of it as a 4-step recipe for creating total confusion. So let's break them down, one by one.
Step 1 is SubBytes. It's a really simple but incredibly powerful substitution. Every single byte, so every single ingredient on our tray, gets swapped out for a different one. And it does this using a fixed, unchangeable master lookup table. It's kind of like having a secret cookbook that just says, anytime you see a tomato, you have to replace it with a carrot. No exceptions.
Next up, we've got ShiftRows. Okay, so we've swapped out all our ingredients. Now we're going to shuffle their positions on the tray. The top row, it stays put, but the second row gets shifted 1 spot to the left. The third row gets shifted 2 spots, and the bottom row gets shifted 3. It's a simple little rotation that does a fantastic job of spreading all the data around.
All right, step 3 is MixColumns, and this is where things get really blended up. Each of the 4 columns is taken on its own and shoved through this mathematical blender. The values inside each column get mixed together in a really complex way, so the bytes that come out are completely different from the ones that went in.
And finally, we have what is arguably the most critical step of all, AddRoundKey. Here, a unique piece of the main secret key, you can think of it as our secret spice for this specific round, is mathematically mixed in with our data. This is what makes the whole thing truly secret. And because a different spice is used for every single round, the process is never, ever the same twice.
Okay, so we've seen this really complex, multi-step process. But as digital detectives, how on earth are we supposed to spot this intricate dance happening inside a program? How do we find the smoking gun?
So let's get right to it. With all of these crazy transformations and shifts and mathematical blenders, what is the one single biggest giveaway that a reverse engineer is looking for? What's the clue that just screams AES is here?
It's this, the Substitution Box, or as it's more commonly known,
The S-Box. So why this? Why is the S-Box the big clue? Well, remember that first step, SubBytes, and that secret cookbook we talked about? The S-Box is that cookbook. It's a predefined 256-byte table of values that is a constant part of the AES standard. So any program that uses a standard implementation of AES has to have this exact table stored somewhere in its code. It is quite literally a digital fingerprint. And this is it. This is the fingerprint. This exact pattern of numbers is what a digital detective is hunting for. An analyst can literally just scan a program's binary data, searching for the specific sequence of 256 bytes. And if they find this table, well, that is an incredibly strong sign that they've just found an implementation of AES.
Okay, I think it's time to file our report and officially close this case. So what did our investigation actually uncover about finding this master code?
Here's the final debriefing. First, AES is an absolute powerhouse of a block cipher that gets its strength from running data through multiple brutal rounds of transformation. Second, each one of those rounds has 4 core jobs: substituting, shifting, mixing, and adding in a piece of the key. And third, this is the most important part of our mission. The single most reliable clue, the smoking gun for identifying AES, is finding its unique and unchanging 256-byte S-Box.
And that just leaves us with a really fascinating thought to chew on. The design of AES, one of the most trusted security systems on the entire planet, is completely public. Anyone can go read it. Its security doesn't come from a secret method, it comes from a secret key. And it kind of makes you wonder, if the blueprints for the world's strongest lock are just out there for everyone to see, what other incredibly powerful secrets are hiding right there in plain sight?